What's going on, PreCalc? Here we are with 1.9. Talking about inverse functions today. Okay, so recall that a function can be represented by a set of ordered pairs. For instance, f of x equals x plus 4. Okay, from the set A, 1, 2, 3, 4, can be represented onto the set B, 5, 6, 7, 8. Just the x's from A plus 4. And there they are, 1, 5, 2, 6, and so on. In this case, by interchanging the first and second coordinates of these ordered pairs, you could form the inverse function. It is a function from the set B to set A. So the inverse of x plus 4 would be x minus 4. You're undoing the plus 4, so you're going to minus 4. And you'll see that it's just a flip. 5, 1, 6, 2, 7, 3, 8, 4. The domain of f is equal to the range of the inverse, and the range of f is equal to the domain of the inverse. Also note that the functions f and f inverse have the effect of undoing each other. Let's see if we can zoom in on that graphic for you. Okay. So domain of f, also the range of the f inverse. So if I do this, add 4, and then I do the inverse, boom, minus 4, I'm back to x. They undo each other. Or if I subtract 4, and then add 4, again, I'm back to x. They undo each other. Alright, so in other words, when you form the composition of f and f inverse, this is what happens. If I do f of f inverse, x minus 4, and then add 4, I get x. Or if I do f inverse of f, x plus 4 minus 4, it gets back to x. Okay, so they undo each other. Find the inverse of 4 times x. That would verify, and then verify both ways, f of f inverse and f inverse of f, to verify they are equal to the identity function. Just they take it back to x. Alright, so 4 times x, let's not think too hard here. The inverse should be x divided by 4. Okay. Alright, f of f inverse of x. So f of x over 4. So if I put x over 4 in there, 4 times x over 4, the 4's would cancel out, and we're right back to x. What if I do f inverse of f of x? So f of x was 4x, and I put that into here, x over 4. Again, the 4's cancel out, and we're back to just x. So yes, indeed, this is the inverse function. Alright, again, another definition here of an inverse function. Let f and g be two functions such that f of g of x equals x, and g of f of x also equals x. Under these conditions, the function g is the inverse of f. The function g would be denoted by f inverse, read f inverse. Okay, we can write it like that. The domain of f must be equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. Okay. These teeny tiny things are probably screen grabs right out of your book, so you can check that out if you decide that later on you want to read that again. Which of these functions is the inverse of 7x plus 4? How can you tell? Okay, so think about this. 7 times x plus 4. Think about which one would be the inverse. Okay, I'm going right here. 7 times x, so I know I need to be doing some sort of division of 7, and then plus 4, I'm going to guess that we have to have a minus 4 aspect in there. Okay, if it's something small like this and you can read it out loud to yourself, 7 times x plus 4, you can kind of reverse it and also go, like, undo it and then do the opposite. So 7 times x plus 4. The last thing I said was plus 4, so in the inverse, I'm going to do x minus 4. 7 times, all right, and then now divide. So you kind of got to walk it backwards and then do the opposite function. We're going to show you a different way, probably a more mathematical way, an algebraic way to do it here in just a minute. But if it's something small like that, you can kind of talk your way through it. 7 times x plus 4, so x minus 4, divide by 7. Graphs of inverse functions. The graph of function f and its inverse f inverse are related in the following way. If the point AB lies on f, then by definition, point BA must be on the inverse, and vice versa. This means, all right, think back to your reflections, A comma B, B comma A. Okay, that means we're reflecting over the line y equals x. Sketch the graphs of the inverse functions 2x minus 3 and half times x plus 3. So again, 2 times x minus 3, so x plus 3 times a half or divide by 2. And that's in parentheses, so that's going to both, so that's the same thing there. Instead of graphing them on this paper, guys, we're just going to graph it on the calculator, and we'll see what the difference is and how they look. So we have 2x minus 3 and 0.5 times parentheses x plus 3. Okay, there's that one. So the other one should be flipped up to here, probably somewhere. All right, and ours isn't going to look exactly perfect because, you know, negative 10 to 10 vertically is a lot. It's more scrunched than negative 10 to 10 horizontally, so mine's not going to be perfect. And let's even throw in the y equals x line. We'll even throw in the y equals x line that we're reflecting over. We can kind of see that. X. And then I think we have a zoom square maybe that we can look at too. So it might look a little, it'll be easier to see the actual reflecting. Because otherwise this looks a little skewed. Alright, you can kind of see where they would be reflected over the black line there in the middle. Let me see if we have zoom square. There's zoom square. Hopefully this squares it up a little bit. So this should adjust it a little bit, make it more of a square or more evenly spaced, make it more obvious. Yeah. Alright, so there they are in the, I don't know if you can see the difference here in the color. The red line, the blue line, and those are being reflected over the black line there in the middle. Okay, one-to-one functions. The reflective property of graphs of inverse functions gives you a nice geometric test for determining whether a function has an inverse. This test is called the horizontal line test. A function f has an inverse function if and only if no horizontal line intersects the graph of f more than once. If no horizontal line intersects the graph of f at more than one point, then no y value would be matched with more than one x. This is an essential characteristic of what is called one-to-one. So we're used to testing for functions using the vertical line test, making sure that no x goes to two y's, and it's okay if one y goes to two x's to be a function, but to be a one-to-one function and make sure that you have its own inverse, when you flip-flop domain and range, now I can't have that one y value going to two different x's. I can't have 1, 3 and then later on have like 7, 3, because now when I flip domain and range, now those 3's are happening twice in the domain of the inverse. Okay, So if you're going to be a function that has an inverse function, you're going to have to pass the vertical line test to be a function the first time. All right, and then when you flip domain and range, your range would now be the domain. All right, so that would be your horizontal line test on the original. If you can kind of visualize all that. Okay, so here you go. Here we have x to the third minus 1. Does this function pass the horizontal line test? I don't think I can draw any one horizontal line that would intersect more than one point. So yes, it will pass the horizontal line test. What does that tell me? Okay, that tells me that it does have an inverse. All right. Probably x plus 1 and then a cube root over the top of it. Opposite of that, so we'd have x plus 1 and then a cube root over the top of it. Okay. The graph of the function x squared minus 1. All right. Ooh, a horizontal line goes through 2 points. So it does not pass the horizontal line test. No inverse. But you're like, wait, Mr. Handke, what about just x plus 1 square root? What about that? Why isn't that the same as that? Okay, because when you're doing the square roots, or fourth roots, or sixth roots, even roots, we got to worry about negatives under here. Don't have to worry about negatives under here. It comes out nice. Negatives under here, now we get into imaginaries. Okay, so that's why we're going to have a plus and a minus. If you would split it up into 2 pieces, you could do this. But there's not one individual function that would be the inverse of this. You'd have to split it up into 2. Because otherwise, if you would do that, it's going to go sideways like this. All right? And now it's not a function. So you're not going to have any one thing. You're going to have to split it up into 2 branches. This piece and that piece. So there's not one individual function, so it doesn't have its own singular inverse. Finding an inverse function algebraically. Here's the fun stuff. This is probably the mathiest stuff. The rest of the stuff we were just kind of thinking about things. Okay, now we're actually getting down to doing math with it. Use the horizontal line test to decide if the function has an inverse. Okay, that could be step 1. You can't read this. Let's zoom in. All right, here's the main steps. Replace f of f with y. So now it's y equals something. Now flip-flop the x and the y's. Okay? And then solve for y. And then now replace y with f inverse. Okay? So step 1, we need to verify, number 1, that this passes the horizontal line test on the original graph. Parentheses 5 minus 3x divided by 2. That whole thing divided by 2. Yeah, that should be a line, right? 2.5 minus 3 half. Yep. So it's a line. Yeah, it's going to have an inverse. Okay? It's going to have an inverse. All right, next. Y equals 5 minus 3x all over 2. Zoom out a little bit so we can see my work. Okay? Next step. Trade your x and y. Put x over here. A little close together. Poor choice. Should have left more space. 3y over 2 and solve. That's not over there. All kinds of mistakes, Mr. Handke. Okay, that 2 is only over here. Okay. X equals 5 minus 3y over 2. And resolve for y. So we're going to multiply that 2 up. X equals 5 minus 3y. Oh, it's going to be tricky here in this step. We'll see. Minus 5 minus 5. Okay, you just see it there. Now we're going to divide by negative 3. So y equals negative 2/3 x plus 5/3. Okay, and then the directions here specify for us to verify it. If I remember correctly, there is a problem like this on the quiz and test. At least there was last year. I imagine there will be something similar to that this year, where you have to do this and then show it both ways, please, both ways, f inverse of f and f of f inverse. All right. So I'm going to kind of leave this space down here for the next example. We're going to go up. So f of f inverse. So f inverse is this. So all of this goes in place of the x in the other one. So 5 minus 3 times all of that, negative 2/3 x plus 5/3. Divide by 2. So negative 3 into both of those. Well, 3's cancel out, negative, make this a positive 2x. And then this is going to be negative 3 times 5/3. The 3's would cancel out and leave it with a negative 5. Oh, this is a positive, isn't it? Negative times a negative is a positive. All over 2. Plus 5 minus 5. 2x over 2. 2's cancel out, and we're left with x. And that's what we want. Now I got to go the other way. F inverse of f of x. So we're taking the original, this, and putting it in for the x spot over here. Negative 2/3 times 5 minus 3x over 2. So this one might be a little sloppier. This one might be a little yuckier. I'm going to split this up into 2 separate fractions, I think. Otherwise, it's going to get a little unpleasant. Oh, I forgot my plus 5/3 out here. Okay, so we got negative 2/3 times 5/2 minus 3x over 2 plus 5/3. Okay, so I multiply this into this one. The 2 and the 2 would cancel out. We're going to have a negative 5/3. Then I multiply this to this. The 2 and the 2 cancel. The 3 and the 3 cancel. The negative and the negative cancel. Plus x. And there's plus 5/3 on the back still to cancel out this negative 5/3. And we're left with x. It all worked out. All right, that was a lot. Yuck. A lot of stuff going on. Lesson learned there. I left all this space empty. Because look, oh, here's the equation. It's going to go straight down from there. Wasted all that empty space. I had to use all this. Okay? So let's see if you can do this one. The cube root of 10 plus x. Find me the f inverse. Ready, set, go. Go ahead and push pause and do that one on your own. Okay, welcome back. Let's check it out. Cube root. So if you can't remember how to find the cube root, I think it's math. There it is, the fourth one. If it's something bigger than a cube root, you'd have to have like the fifth root. Type the number 5 in first, or 6 in first, or whatever it's going to be, and then come into x root. Okay, but cube root of 10 plus x. Graph that. Yep. Okay, that's going to pass the horizontal line test. So we should be able to come up with one. All right, y equals cube root 10 plus x. Okay, switch the x and the y. X equals cube root 10 plus y. Alright, now get y by itself. Solve for y. I got a big cube root going around everything, so I'm going to cube both sides. So x cubed equals 10 plus y. Subtract the 10. X to the third minus 10 equals y. Y equals x to the third minus 10. Okay, there's your inverse. You can go ahead and test it out. Verify, it should come out nice. Alright guys, there you go. There it is, you're on your way. Check out that problem list for section 1.9 and let me know if you have any questions. Thanks a lot.